Okay, great. Hopefully you guys can see my slides also, and you are using your brains to think about the favored chair conformation between the couple that I've posted here. So everybody take a couple minutes to think about that while everybody else is joining. Let me make sure there's nobody stuck in the waiting room. Oh, there's one person stuck in the waiting room. Okay. Okay. All right, so happy Friday, everybody. Let's go ahead and get started with using our brains on some of the things that we were thinking about on Wednesday together. So I've got a couple different either or questions for you here. So let's get started with the one on the top. First of all, take a look at this for yourself and confirm for yourself that you can see that these are the same molecule. They're the same molecule. They are just two different chair conformations. So all we've done between this one on the left and this one on the right is to rotate around the carbon-carbon bonds of the ring structure. So once you have yourself convinced of that, take a look and let me know which one do you guys think is the favored chair conformation here. Is it the one on the left or the one on the right? Awesome. Good job, guys. It is the one on the right. The one on the right here has both of the substituents in an equatorial position, and that is going to minimize the sterics involved. So if you remember, the equatorial or the equator around that cyclohexane gives those substituents more space. And you can kind of even see that here. You can imagine these shooting off like rays out of the sun, right? Whereas in the axial version, these two axial substituents are pointed straight up. And so these are methyl groups, right? So each of these is going to have hydrogen atoms coming off of it. And so you can easily imagine how those hydrogen atoms would be bumping into the hydrogen atoms of the other methyl group here. Okay, what about the bottom set here? Now we have something that's a little bit different. So instead of both of our substituents being on the same side of the ring, so that they're either both axial or both equatorial, at the bottom, we have to choose. We have one situation where you have an axial methyl group and equatorial ethyl group. And in the other flipped chair conformation, we have an axial ethyl group and equatorial methyl group. So do the same thing you did up here. First, take a look at these two chair forms and convince yourself that you can see that these are the same molecules, right? The footrest of this chair on the left here, which is pointed down, is the same carbon as the headrest of this chair on the right over here, which is pointed up. And so in the sort of two carbons over from that, we have an ethyl group, and two carbons over from the footrest over here, we have an ethyl group. So now we've convinced ourselves these are the same molecule, just a chair flipped version of it. So which one is favored here? Yeah, good. You guys are on your game today. It is indeed the left version that's favored. And again, the dictating factor here is sterics. Because an ethyl group is bigger than a methyl group, that ethyl group will determine which chair conformation is favored. And that ethyl group, because it is bigger, will want to be in the equatorial position. And that's the situation that we have with the chair form shown on the left. Okay, cool.
Can I ask a question about the chair form on the right in the bottom?
This one, yeah?
So that substituent, even though it's like kind of angled off to this side.
You're talking about this, right?
Yeah, that's still like axial, even though it's like a little not straight up and down.
It is still axial. So you can see, let me draw on the slide. Okay, this is the axial position. The equatorial position on that carbon would look like that. I'll go ahead and put a hydrogen there so we can make sure that we understand that's a hydrogen. And then this one, the axial position would be here with a hydrogen. So it is angled just a little bit, but you can also see that the chair itself is drawn a little bit more flat or whatever. I don't know exactly the right term for it, but you know, we've been looking at a lot of chair forms that look like that. Mm-hmm. this arrow here is kind of more pointed upwards, and I've been drawing these as directly upwards, but you can imagine this is all sort of like dependent on the artistic skills of the person drawing, right? And it is a little bit hard to tell, and you can see also why it's hard for us to tell when we grade your all's free drawing. It's a little bit hard to tell as well. But what you want to be sure to do is make sure that if you imagine like a plane at the apex of this carbon right here, your axial one is going to be going up above that. So okay. I drew this for you guys before, but if we look at two different tetrahedral molecules where we hold something upright, there is one version where we have this bond that's vertical, the other three substituents would be down. The other way to look at it is a bond that's vertical the other way with the other three substituents up. And you can see how it kind of has like an umbrella turned inside out look to it, right? Mm-hmm. So if you're ever in doubt when you're drawing your own as to whether or not your artistic skills are clear enough, one thing that you can always do to help is if you want to write in the other substituent and put a hydrogen there, you know what I mean? Sometimes it's easier to tell that, for example, this ethyl is axial if you can see where the equatorial one is positioned.
Okay, cool. Thank you.
Hopefully that helps. Okay, and someone's written in the chat box, the position of the substituent with the most carbons is the deciding factor, in which is the one that's most favored. Okay, sort of, but it's not just the most carbons. In this case, in this example, it's true that the biggest substituent has the most carbons, but I will draw you a different example where if you had a situation where you had a tert-butyl group like this versus, so that's got 4 carbons, right? 1, 2, 3, 4. Versus like a hexyl or octyl group that's linear. That hexyl or octyl group would have more carbons, but because it's not as bulky and big, I actually don't know which would be the right answer here. I would never ask you guys a question like this, but it's just keep in mind, it might not be the number of carbons, it would be the overall size because we're talking about sterics here. Okay. So that kind of referred back to chapter 3 material, which we finished up last class. So today what I want to do is get a really good jump on chapter 4. We're going to make it hopefully at least halfway, if not farther, through chapter 4 chapter 4 material today. So before I do that, just a couple of quick announcements for you guys. I did post an Achieve assignment related to chapter 4, and that is going to be due Wednesday morning next week at 9 a.m. We are going to have a quiz on chapter 4 on Wednesday of next week. It will be during class time, and I will give you more details about that on Monday, whether it's going to be at the beginning of class or at the end of class. I'll let you know on Monday. But just be prepared that we will be using part of Wednesday's class for the quiz, and the other part of Wednesday's class we will use for other material. I am going to include, this is going to be a predominantly chapter 4 quiz. It will cover all of chapter 4 because I will finish chapter 4 on Monday. But I am going to include 1 or 2 questions on chapter 3 since we didn't quite capture all of chapter 3 on exam 1. It shouldn't be that much of a surprise to you about what kind of a question that will be given what we spent our time on in our last class together and what we just did those brain exercises on. Exam 1 scores, there were just a couple of loose ends that I needed to tie up because of some folks who had technical difficulties with their part 2. These should be posted this afternoon, so you guys will be able to look at not just your raw scores, but the answers to all of the part 1 and part 2 material later today. And just a couple of notes in general, kind of where we are in the course. I wanted to remind everybody, if you did really well on exam 1, good for you, and don't let up. Don't take your foot off the gas here. Keep the pressure on yourself to stick with the material and keep on keeping up. If you didn't do as well as you had hoped to on exam one, I just want to remind you guys about all sorts of resources that are available to you, in addition to the studying you're doing on your own. So of course you can stop by my office hours, and I really like that because I like getting to know you guys, and I don't have very many opportunities to do that because of the nature of our course being online and being big. But so please stop by my office hours. The SI sessions are Monday and Wednesday evenings, and also Thursday in the middle of the day. I believe Monday and Wednesday are in person in Hoops Hall, and Thursday is online. So hopefully you guys are taking advantage of these opportunities already. And then there's also additional opportunities if you guys want or need them. The Campus Learning Center, the CLC, in addition to organizing SI, like they're the ones who fund and organize the SI program, they also have a lot of other resources. So you can sign up to have one-on-one peer tutoring sessions with students who have taken this course in the past and done well in it. You can read more about that here, how to sign up and such. And there's also drop-in tutoring sessions at the Campus Learning Center. So it kind of doesn't matter when you're working on your orgo studying and your orgo homework, there is somebody available to help you a lot of the time. So these hours that I've posted down below, these are not the hours that the CLC is open. These are literally the hours that somebody is there for this course specifically. So that's a lot of different opportunities where if you guys are between classes and you have a question that you want answered or whatever, you can drop into the CLC and there will be somebody there who can help answer your questions. So I do want to kind of make the point here that I am trusting you guys, and you guys need to be responsible on your own to take the feedback that you're getting on your quizzes, on your exams, on the in-class participation problems. You guys should be looking at those, and if you got something wrong, make sure you understand why you got it wrong. Make sure you understand the concepts associated with it so that when that comes up on the next exam or on the final exam, you will have that resolved for the next time. So this whole point of being in college, the whole point of this class is to learn. And sometimes the best way to learn is from our mistakes. So hopefully you guys are learning ahead of your mistakes more often than not, but if you do make mistakes on a quiz or test, don't beat yourself up about it. Just make sure you understand it for the next time. Okay, with that, let's jump into actual chemistry land and let's cover some material for chapter 4. So chapter 4 is the study of chemical reactions. And what we're going to do in chapter 4 is introduce just one reaction and then use that one reaction as a platform to talk about ways that chemists study reactions, mostly related to thermodynamic concepts and kinetic concepts. So before I do that, this actually isn't a reminder, that's a mistake, that's from a different section. Before I do that, I'm going to just want to take a moment to do a kind of an overview, bird's eye view of what we mean when we're talking about studying chemical reactions. So I want to put this in context of where we've been and where we're going. Up until now, chapters 1 through 3, we've been talking a lot about geometry. We've been talking about the shapes of molecules. We've been talking about the hybridization around an individual atom and therefore the shape around that atom. We've been talking about the polarity of bonds, and so where electron density lies within a bond. And all of those things have very structural connotations. And we haven't really seen a lot of action, right? Like the most action that we've seen before is in chapter 2, we saw some protons moving around, but they're just protons. That's kind of boring. And we've also seen now some rotating around sigma bonds. But again, that's like motion happening within a molecule. That's not really interactive and not really exciting. So now we're going to be moving on to a new kind of phase of this course where we're going to talk about reactions. And of course, when we're talking about reactions, we're talking about things that are more exciting than just structures of molecules. But I want to point out that structure is still important. The structure of a molecule, the electronic nature of that molecule, is going to give us some insight into how that molecule is going to be likely or unlikely to interact with another molecule. Whether a reaction is likely or unlikely to occur has everything to do with what the two partners in the reaction are and their structure and the electronic nature of the features within them. So of course we can think about reactions as being exciting, explosive reactions or colorful reactions that bubble all sorts of crazy, weird foam out. In organic chemistry, most of the things that we're going to do are not going to look like this and hopefully not look like that either. Most of the things in organic chemistry are kind of yellow or brown or off-white or clear. These fun colors, you really have to take inorganic chemistry to get to play with the really fun colors. So just a pitch for kind of keeping on in the chemistry track if you want to play with fun colors that look like this. All right, back to chemical reactions. So what am I talking about when we're talking about chemical reactions? Well, at its core, at the base of this, we're talking about reactants or starting materials that become something else, they become products. And one of the questions that we really want to know is, how likely is that to happen? What is the likely outcome when we put two things together, right? Is it going to look like this, or is it going to look like that? So we want to be able also not just to know what the likelihood or the not likelihood is, but we want to know about how that's going to happen. We want to be able to understand the energy changes that are involved, and we want to be able to understand also the reaction rates that are involved. And in order to kind of put all of these things together, one of the tools that's really useful to chemists is understanding what's called mechanism. And I sort of started introducing this concept to you guys in chapter 2 when we learned about curved arrows. But here we're going to get into it more, and it'll keep coming back up again and again. What I mean by a mechanism is a step-by-step, very detailed description of how we go from reactants to products. And keep in mind, chemistry is really about what's going on with the electrons, right? So the electrons are going to be doing all of the work. And we have these curved arrows now that can show us what's happening with the electrons. They show us how the electron density starts in one place and it moves to another place. So just a reminder that the arrows, the curved arrow notation helps us depict that, and that the directionality of those arrows is really important. Again, you're going to hear me say it again and again. Structure is important because that's going to give us insight into how molecules interact with each other. Mechanisms are also important because how a set of reactants becomes the products will help us figure out what products they become, right? So if we have a set of reactants that starts in one phase and it follows a path that's stepwise, it might get to a set of products that are different than if it followed a path where all the electrons were moving at the same time. And we'll see some of the consequences of different mechanisms as we move through this course. For our first reaction, what we're going to use as a model reaction is the chlorination of methane. It's an example of a free radical chain reaction. And what I mean by this, two aspects of the name here. One is the free radical aspect. That means there's going to be an unpaired electron involved in most of the steps of this reaction. And the other aspect of this is that it's a chain reaction. So this should invoke in you guys images of like dominoes falling over. What that means is that once we get that reaction started, it will regenerate and kind of go through a cycle on its own. And you'll see what I mean by that as we go through the slides. I want to remind everybody, because we are going to be talking about mechanisms, that we know how to use curved arrows, but for free radical reactions where we're moving single electrons at a time, we're going to use single-headed arrows. And just to remind everybody, these are very different than most of the arrows that we use in organic chemistry, because most reactions involve two electrons moving together at the same time, in which case we would use a normal arrow with a normal arrowhead. But for whatever reason, your book, the authors of your book, have decided to start off your entry into organic chemistry reactions with a very unusual type of reaction that's a free radical based mechanism. This is not the normal typical type of reaction, but this is the reaction that your authors of your book have decided to use to demonstrate concepts of thermodynamics and kinetics. And so because I've told you guys I'm going to follow this book kind of as it comes, that's what we're going to do too. Okay, so I'm going to talk about the chlorination of methane, which again is an example of a free radical chain reaction. I'm going to talk about it in excruciating detail, and we're going to go over the mechanism of it, and we're going to understand where every electron is and where every electron is moving to. And then we're going to use this reaction to talk about thermodynamics, and if we have time today, a little bit about kinetics, but definitely about thermodynamics today. So first I have to introduce you to this reaction. So this is the overall reaction that we're going to be talking about today, the chlorination of methane. So what do I mean when I say the chlorination of methane? Well, here's methane, CH4, and the overall reaction here, you'll see we're going to be replacing one of the hydrogen atoms of methane with a chlorine atom to get chloromethane or methyl chloride, either word is fine. And we're going to do that using molecular chlorine or Cl2. And we have to involve some heat or light to get this reaction to go. So what I'm showing you here is called the overall reaction or the overview of the reaction. It doesn't tell you anything about how this reaction happens, about how this bond gets broken and how this bond gets formed, what order things happen in. Overall, we can see we need to break this bond and we need to break this bond. And we're going to make a new bond between carbon chlorine and a new bond between hydrogen and chlorine. But we don't know how we're going to do any of those things or what order they go in until I tell you. So another couple of things about this reaction that I want to point out, I mentioned it does require heat or light. And then also that if we have just one photon of light, so if we have just a little bit of light, we can use that one photon of light to generate a lot of products. And that's the chain reaction part, the chain reaction aspect of this reaction. So we're going to use just a little bit of heat or light to get things started. And then once we've gotten things started, they're going to kind of keep going on their own, like a self-fulfilling prophecy kind of. And you'll see what I mean by that when we go through the mechanism for this reaction. So it's going to be broken down into three kind of phases, if you will. The first step that needs to happen, or the first phase, is called initiation. And that phase of the reaction, we're going to take the starting materials that we had and the reagents that we had, and we're going to generate a radical intermediate. That's the initiation phase. The second phase is called propagation. And in that phase, that's the bulk of the reaction. It's the propagation phase. And what happens there is that the radical that we generated during the initiation phase initiates or starts a series of chemical reactions that produce a new reactive intermediate and a product molecule. And those go on in a cyclical fashion to generate a lot of product molecules. And again, that'll become clear when I show you the mechanism. The third phase is called termination. And termination is basically the word that we're going to use to describe what happens when we end the life of these radicals. So we're gonna quench the radicals or destroy the radicals by having two of them combine or having them combine with other things. And you'll see some examples of that on the next couple of slides. So step by step, mechanistically, here's what this free radical chain reaction looks like. During the initiation phase or the initiation step, the molecular chlorine will be broken so that there's no longer a sigma bond between the two chlorine atoms, but instead it will become two chlorine radicals. So what I'm saying here is that the sigma bond between these two chlorine atoms is going to break in such a way that one electron goes with each chlorine atom. The driving force for this is light or heat. So light and heat are forms of energy, right? So basically we're putting a little bit of energy into this bond to disrupt it and break it. So we're adding energy in here to break the chlorine-chlorine bond and break the molecule in half perfectly so that we have then two atoms of chlorine, each of which carries an unpaired electron. So all of the time, anytime in organic chemistry that you find yourself looking at an unpaired electron, you should know that those are unstable species. Those are reactive species. There are very few radicals or free radicals out there that are stable and content to just hang out on their own. So when we take our chlorine and we break that bond homolytically, this word homolytically I'll talk about a little bit later today, but it just means one electron from the bond goes with each chlorine atom. When we break that bond homolytically, we generate these two radical chlorine atoms. I also want to take a moment and point out that these chlorine atoms, we can draw them showing all of the lone pairs, or we don't have to show all the lone pairs because all of us as chemists now know where lone pairs are based on our Lewis structure rules and our octet rules and our formal charge rules. So we can see that we have a chlorine atom. If we draw it like this, all of us should know that there are 3 lone pairs here. They're just kind of sitting there and not doing anything. We can't, however, not show the radical. We always have to show the unpaired electron if there's an unpaired electron. So the same thing with bromine, we don't have to show the lone pairs, but we have to show the unpaired electron. You always want to, in general in organic chemistry, you always want to be able to show the areas of the molecule where exciting things might happen. So again, the hydroxyl radical, we don't have to show the lone pairs. We could just show the single radical. So it's okay to draw it this way, but it's equally okay to draw it like you see down here. And it doesn't have to be just kind of the upper right corner of the periodic table. We can also have carbon-based radicals. So you can see this methyl radical here, which can also be drawn as a CH3 with a dot over the C. You can see how we still have to show that unpaired electron because that's one of the key and important pieces of this methyl radical. What is the formal charge on that carbon atom? So none of these radicals that I'm showing on the slide here have a formal charge, right? So this carbon atom has 3 bonds to the 3 hydrogen atoms, and it has 1 electron. So we've counted up 4 things, if you like the thing method of counting for formal charge, and carbon has a valence of 4. So we're all set with that carbon. There's no formal charge. Likewise, chlorine atom, to answer John's question, chlorine has the 1 unpaired electrons and then 6 electrons that are in lone pairs that are hiding here or understood to be there. So chlorine radicals do not have a formal charge. Just because they don't have a formal charge doesn't mean they're stable, right? All radicals, all unpaired electrons are going to be unstable and reactive. Okay, so let's move on to the next step. So we just did the initiation step where, again, we're going to take our molecular chlorine, or Cl2, and we're going to break that bond so that 1 electron goes with each chlorine atom. And you can see, again, we're using our little half arrowheads to demonstrate single electron movement. When we move on to the propagation step, here is the chlorine atom that we generated from the initiation step, right? This chlorine atom is going to interact with a molecule of methane, and it is going to initiate bond breakage between the carbon and the hydrogen. It's going to do what we call hydrogen atom abstraction. So what that means is that it's going to be taking a hydrogen atom, so the proton with its electron, so an H dot, and it's gonna make a new bond. So it's gonna take the one of the 2 electrons of the bond that was between carbon and hydrogen and the unpaired electron from chlorine, and that's how you're gonna get this new bond here. And that's represented by this pink arrow and this pink arrow. So 1 electron from the bond is going to come together with the unpaired electron from the chlorine to make this new bond. Well, what happened to the other electron that was in the CH bond? Well, it's going to go back and be now a new free radical on that carbon atom that you can see here in the direct product of these arrows. So just to drive this point home, I want to make sure everybody's clear on this. In this reaction, we are taking off an H atom. So the nucleus, which is a proton, and the electron of an H atom. This is not an acid-base reaction where only the proton is moving without any electrons. This is a whole hydrogen atom represented as H dot or a proton and an electron. So someone has asked in the chat box, is it necessary to have the arrow from the CH bond to the C to show that the electron is there still? And the answer to that is yes. This arrow, this little arrow right here, is absolutely part of the mechanism, because what you're essentially saying here with these arrows that you had two electrons that were in a bond, and you have to account for what those two electrons do. One of those electrons went and made a new bond, but that other electron, it is not still in a bond because there's no bond there anymore. So that second electron has to leave the bond and go into then an orbital on the carbon atom. Okay. Also, again, here, we're moving only single electrons around. So they might become pairs of electrons, but one electron came from this bond and one electron came from over here. So we're using our single-headed arrows here. Okay, in the second step, so we're now on to the second step of propagation. We have the methyl radical that we just generated in our first step. That methyl radical is a radical. It's an unpaired electron, so it's highly reactive. It is not very stable. And that methyl radical will combine with a chlorine molecule, a new molecule of chlorine, so Cl2. And this methyl radical will cause this chlorine-chlorine bond to break. One of the electrons of the bond from chlorine-chlorine makes a new bond with carbon. The other electron goes and lives on the chlorine atom to give you another chlorine radical. So if you notice what we just did here, one of the major things that we did was that we made a new molecule of our product, right? So this product is the chlorination of methane. So if you look here, we just did it. We just chlorinated our methane. So we've generated one molecule of our target product. The other thing that we did that's really important is that we regenerated a chlorine radical, a chlorine atom carrying an unpaired electron that can then go back into the beginning of the propagation step and react with a fresh molecule of methane to do that first propagation step again. I'll put this all together for you in a kind of an overview slide in a couple slides here. The last phase of this reaction is called termination, right? So in a termination step, this is going to be any time we have two free radicals that join together to end up giving us a compound that does not have any unpaired electrons anymore. So one version of this is if we have a methyl radical and a chlorine radical, these two can come together. And that actually gives us a molecule of our product also. So an important note here is that I've presented this as initiation and then propagation and then termination. But these things are kind of all happening at the same time, right? It's not as neat and tidy as this and then this and then this. They're kind of in this big pot of molecules. You've got some chlorine molecules that have been initiated into chlorine radicals, and they've gone around and reacted with things. So there might be a case where a methyl radical and a chlorine radical are nearby each other. And if they are, they might bump into each other and create this new bond. That's one way to terminate or quench two radicals that happens to give us the product. But it's not the only way that we could quench radicals. There's a lot of other ways that can destroy the radicals if they run into the contaminant or another reagent or even the wall of the flask. So here are just some other examples. We could have two chlorine radicals coming together. That could happen. Of course, that would regenerate one of our starting materials that can go then and keep participating in the reaction. We could also end up having two methyl radicals come together. That would generate a molecule of ethane, which would be a byproduct in this reaction. Either of these two original radicals could also collide with some contaminant in your reaction or the side of the flask even, and end up quenching in that way. So all of these things are possibilities for how to terminate the reaction. Okay. The next thing I want to do is try to put this all together for you and help you kind of connect the dots that we've gone through over the last 10 or so slides. Here's the overall reaction again, the same thing that I showed you a couple of slides ago, where we're going to take methane and turn it into chloromethane. So Now we know how we're going to break these two bonds, and we know how we're going to make these two bonds. We know what order they go in, and we know what it looks like. So first, we need to create a chlorine radical. That's the initiation step, where we take light or heat and we break that chlorine-chlorine bond to get a chlorine radical. Then in the first propagation step, we're going to make a new bond between the chlorine atom and this hydrogen atom. So another way to say this is that the chlorine atom will abstract a hydrogen atom from methane. When we do that, we're breaking the CH bond such that one of the electrons helps to form this new bond between each Cl. The other electron goes back to the carbon of methane to give a methyl radical. And we can see here, we've actually generated one of our two products from this reaction in this step. In the second propagation step, the methyl radical that we just generated will combine with a new fresh molecule of chlorine to create a new carbon-chlorine bond using one of the electrons in this chlorine-chlorine bond. The other electron from that chlorine-chlorine bond will go back to the chlorine atom to generate another chlorine radical. So now we've generated a molecule of our target compound, one of our products, and we've regenerated a new molecule of chlorine as a radical. That chlorine radical that has been regenerated can go back to another molecule of methane and start this process over and over again. So with one photon, where we generate, two chlorine radicals with one photon, we can then just keep going around and around and around and around and around and around this cycle to generate a whole bunch of chloromethane until we terminate all of our radicals just because they happen to run into something else that could terminate them. Okay, so that's the overview of the free radical chain reaction. For the rest of the time today, I'm going to talk about thermodynamics, mostly thermodynamics, but I'll give you an overview first to kind of put thermodynamics and kinetics into perspective for you. So this is a reaction coordinate diagram. It shows essentially starting materials going to products and the energies involved in these things. So we can see that there's a certain amount of free energy in our starting materials and a certain amount of free energy in our products. And we have to put in some amount of energy to do all of the bond breaking that we have to do. But we may get some of that energy or more than we started with even back when we make the bonds. When I talk about thermodynamics and kinetics, these two things are related to each other, but they're also kind of separate. When we're talking about thermodynamics, we're really asking questions about how much of something is going to get made, which is the more stable, the reactants or the products, and which therefore is going to be favored when we do this reaction. When we talk about kinetics, we're talking about the rate of a reaction. So you can think about kinetic energy, and that's really a question about how fast a reaction occurs or how slow it occurs. So of course, thermodynamics and kinetics are going to come with some math. So I think all of these things are familiar to you guys from previous, but I'm just going to go over them again with you. If we have this generic equilibrium reaction where Y and Z are in equilibrium with each other, Y is going to get converted to Z at some rate that can be described using a rate constant or a little k. And Z will also go convert back to Y using some different rate constant or k-1. These k1 and k-1 values give us the rate forward and the rate backwards for this reaction. We can talk about an equilibrium constant or a big K. The KEQ for a reaction tells us about what that reaction will look like at equilibrium. And you can imagine if Y converts to Z faster than Z converts to Y, then the K1 should be bigger than the K-1. You would have more Z than Y, and your KEQ would be large. So this KEQ gives us the concentration of Z and Y at equilibrium. So it's really going to tell us, does the reaction favor the products where Z is big, or does it favor the starting materials where Y is big, the concentration of Y is big? And if the concentration of Z is big and it favors the products, then KEQ is going to be really large, right? If it favors the starting materials, then KEQ will be a fraction or less than 1. It'll be between 0 and 1. And again, thermodynamics is going to give us a description of what a reaction is like at equilibrium, but kinetics tells us about how fast different reactions are happening. Keep in mind, if something is at equilibrium and it's, say, 20% Y and 80% Z at equilibrium, that doesn't mean there's no reactions happening, right? That means that some of the Y is converting to Z and some of the Z is converting to Y, but the rate at which they do is keeping it so that there's about 20% Y and about 80% Z the whole time. Okay, let's go back to our reaction coordinate diagrams and make sure we've got some terminology down for these different things. Note that the progress of the reaction is the x-axis here, so starting materials becoming products on the x-axis, and the energy, of course, is the y-axis here. So we can make a comparison between the free energy of our starting materials and the free energy of our products, and that's going to become important for some of the thermodynamics concepts we learn about today. At the top of this mountain here is called a transition state. This highest point is a position where we have bonds that are partially broken and partially formed. So in this example, this generic example, the AB bond here is partially broken. The BC bond here is partially formed because of the nature of the reaction. I want to take a moment to point out that up here at the tops of mountains, so our local maxima, are transition states. This is going to become important when we have multi-step reactions, but the valleys are called intermediates. And the difference here is that intermediates have fully formed or fully broken bonds. And so they can, in theory, be isolated. Whereas transition states have partial bond formation and partial bond breakage, cannot be isolated. And again, intermediates are these low points, the valleys on our reaction diagrams. Transition states are the mountaintops. Okay, we're going to take the last little bit of time here and drill down into some concepts of thermodynamics, and eventually we'll get to the point of applying it to the chlorination of methane reaction that we learned about today. So we just looked at a generic reaction of Y going to Z, but in our real world, our reactions are usually a little bit more complex than that. So I need to show you guys the complex version of this as well, where if you have multiple products and multiple reactions, the KEQ involves multiplying those concentrations together. And also, if their stoichiometry of reactants or products is not just 1 to 1 to 1 to 1, then what we have to do is take that stoichiometric cofactor and make it an exponent in our KEQ equation. So just to keep that in mind, that it's not just the concentration of each, but also the stoichiometry that's involved in generating a KEQ. So what is the KEQ for the chlorination of methane that we just talked about? Well, if this is the overall reaction, in this case, we're lucky we do have a stoichiometry of 1 to 1 to 1 to 1, right? So when we write out the KEQ, we have the concentration of the products multiplied by each other, divided by the concentration of the reactants multiplied by each other. And the KEQ for our reaction, the chlorination of methane, is 1.1 times 10 to the 19th. That's a really big number. So think about this for yourself. Take a moment and think to yourself, what does that mean conceptually? Think about it mathematically in terms of this equation, or think about it conceptually for yourself. What does it mean for our reaction? What does it mean for the chlorination of methane? Tons of product. Thanks, John. Yes, the equilibrium for this reaction is hugely favoring the products. What that means is that when we put these things together, when we put methane and chlorine together, if we give it a little bit of light or give it a little bit of heat, it's going this way. It is favoring the right side here, and those products will be favored dramatically. And we'll see why over the course of this chapter. Okay, we've been talking about KEQ, but I want to relate for you KEQ to delta G, or the Gibbs free energy. Hopefully this is a concept you guys have seen before. The delta G for the reaction, so the free energy overall for the entire reaction, can be defined by taking the free energy of the products and subtracting the free energy of the reactants. So what is delta G anyways? Well, it's the energy that it that you either have to do the work or the energy that it takes to do the work. If you have a negative delta G, a reaction is going to be favorable and it's going to be spontaneous. What do I mean by that? I mean that the reaction will occur in nature, in real life. With a negative delta G, that reaction will move forward and go towards products. We can take our equilibrium constant that we know how to define now, and we can relate it mathematically to delta G for a reaction using this equation. This equation, delta G equals negative RT natural log of the equilibrium constant. This equation is an equation you need to know. Let me say that again. You guys need to know this equation. You have to know it. This equation takes delta G and KEQ and relates them to each other. So what do I mean by that? Here are some reaction coordinate diagrams, and this is going to be a visual way to demonstrate the mathematical relationship that I just showed you before. If you have a negative delta G, that means the free energy of your products is lower than the free energy of the reactants. I'm going to go back to the equation just for a second here. Delta G equals negative RT times the natural log of KEQ. I'll post these slides so you guys will be able to write this down and study it from the posted slides. So on these reaction coordinate diagrams, if we look only at the one on the left for a minute, our products are more stable. They're lower in energy. They have a lower free energy than the reactants. So when we calculate our delta G for the overall reaction, and we take our delta G of the products minus our delta G of the reactants, we're going to have an overall negative delta G. This is called an exergonic reaction. This is a spontaneous reaction because it's going to favor the products because they're lower in energy. I also want to point out in this reaction, the KEQ is going to be greater than 1 because the products are favored. They are lower in energy, and so that equilibrium is going to favor the products. And if the equilibrium favors the products, then the KEQ has to be larger than 1. Okay, on the flip side, if we have a different version of that, if our reactants are lower in energy than our products, then this reaction is not favorable. It will not happen spontaneously. It has a positive delta G because we're taking a larger number and subtracting a smaller number. So our delta G for the overall reaction will be positive. Also, our KEQ will be a fraction. It'll be less than 1, between 0 and 1, because the reactants are more stable than the products. So in our KEQ equation, the denominator will be bigger than our numerator. And so we would have a fraction less than 1. So these words, exergonic and endergonic, are kind of weird words, but you do need to know them. And hopefully that you're being able to connect right now kind of intuitively the idea of products being more stable than reactants with the mathematical negative delta G and a KEQ larger than 1. This graph here is going to show us the delta G at what happens to the yield of a reaction at different delta Gs. So we just talked about how a lower delta G favors the products more. So as you get more and more and more negative in your delta G, you actually see an increased yield or an increased conversion to products. And you can see that at some particular delta G, around the negative 12 or negative 16 kilojoules per mole, you get to a point where you have essentially complete conversion to product. But it really relies on getting this very, very negative delta G to get that conversion done. So I'm out of time for today, so I'm going to stop here. I will post all of the slides about thermodynamics. I'm going to ask you guys to flip through all of the thermodynamics slides before next class. And on Monday, we'll pick up with thermodynamics and kinetics, and then we'll apply it to our reactions. So I'm happy to stick around for a couple minutes for questions. Otherwise, keep an eye out on Canvas for your exam 1 scores to pop up later today. And I'll see you guys on Monday. Have a great weekend.